We'll start this videotape by going over the sampled problems on power cycles and entropy. When we finish that, then we'll go on to the typical exam problems. So problem number one, we have two Carnot engines, that's the key word, two Carnot engines in series such that the heat rejected from one is the heat input to the other. The heat transfer from the high temperature reservoir is 500 kilojoules. If the overall temperature limits are 1000 K, 1000 degrees Kelvin and degrees Kelvin, and both engines produce equal work, find the intermediate temperature between two engines. There's some temperature in between these two extremes. Now we start off by defining what we mean by a Carnot cycle. A Carnot cycle has an efficiency which is quite high, and this efficiency is given by the difference between the temperature, the high temperature, and in our case the intermediate temperature, T sub I. This is divided by T sub H. Now this would be for the first engine, the one that's at the higher temperature. Now the second one would start off with T sub I being its high temperature, subtract off T low, then divide this by T sub I. So that would be the second. This would be the first one. Now they both produce, this is efficiency, they both produce, I'll call this N sub 1, N sub 2, and we say that we're given that they do equal work. But work is given by the product of efficiency times the heat in. So this means that W1 is equal to efficiency 1 times Q sub 1, that's Q sub 1 in, and W2 is equal to N sub 2 or eta sub 2 if you want to use the Greek letter eta, and this would be times Q sub 2, whatever goes in. So this would be the key equation which follows from this equation, and this is the one we plan to use to solve the problem. We can replace this equation now, eta sub 2. Now Q2 in is the same as Q1 in. We'll explain why in just a second. Q1 in times 1 minus the efficiency, it's just this part in here, 1 minus the efficiency of the first engine. Why is that so? Because the input to engine number 2 is the output. This is the same as the output of engine number 1. But the output of engine number 1 is the input times 1 minus the efficiency. This should be 1 minus eta sub 1, like this. So we have an equation that says that eta 1 Q sub 1 in is equal to eta sub 2 times Q sub 1 in times 1 minus eta sub 1. These two cancel on either side. Eta sub 1 is equal to the high temperature minus the intermediate temperature divided by the high temperature. This is equal to eta sub 2, which is T sub I minus T low divided by T sub I times 1 minus, and eta sub 1 is the same eta 1 we have over here, which will give us TH minus T sub I divided by T sub H. So here we have a simple algebraic equation. There are only three variables, TH, TI, and TL. We already know the value of TH. We already know the value of TL. TH was given as 1000. And we know that TL was equal to 400. So we can now calculate T sub I from this. It turns out that T sub I turns out to be exactly equal to the average values between TH and TL, which would make this 1400 over 2, or 700 degrees K.